Earth is bracing for a torrent, a river of charged particles racing at nearly 700,000 kilometres per hour, pouring from a rare trans-equatorial coronal hole just as the interstellar comet known as 3I Atlas slips behind the Sun without a hint of warning. Space weather specialists have a name for this alignment of forces: a perfect coupling. The magnetic doorway between Sun and planet stands ajar, and geomagnetic storms can kindle with almost no resistance. At the very same hour, a sudden flurry of powerful earthquakes rattles seismographs around the Pacific Basin, and an argument fractures the scientific community along a familiar fault line. Coincidence or cause? Some wave away any link at all. Others, more cautious, suggest we may be watching a larger cosmic rhythm reveal itself in real time. The official line says these threads do not weave together, but 3I Atlas is interacting with our star in a way that defies easy categories, and when it emerges from the solar glare, the first images may force us to redraw the map. So the first question is simple and not simple at all. What does a solar storm on this scale truly mean for Earth? A coronal hole is not a literal hole in the Sun's surface. It is a region where the upper solar atmosphere thins, and magnetic field lines don't close back in graceful loops, but stretch, unmoored, into interplanetary space. Across most of the photosphere, magnetic fields arch like taut springs, bottling up hot plasma in looping canopies. Inside a coronal hole, those lines open like a gate left slightly ajar after midnight, and the plasma does not drift out. It accelerates, streaming away at extraordinary speeds. In extreme ultraviolet images, coronal holes look like dark, yawning bays that can sprawl across millions of kilometres, sometimes bridging north and south like a shadowed causeway. When a coronal hole straddles the equator, it becomes a trans-equatorial superhighway for the solar wind, tying the hemispheres together and funneling energy straight toward the inner planets. The October 2025 episode began with SDO's AIA instrument imaging an unusually broad unipolar coronal hole that stitched the Sun's two halves together. Magnetogram readings showed the field was predominantly negative and open, an uncommon configuration outside deep solar minimum. That architecture unlocked a high-speed stream measured up to 700 kilometers per second, which punched out of the corona and tore across the inner system. As space weather physicist Dr. Tamitha Skoff likes to say, these regions are the Sun's exhaust ports, places where plasma isn't simmering under a lid, but venting straight into space. Direction and polarity matter. When that open magnetic outflow points at Earth, our planet's geomagnetic shield is forced into a head-on test. That is the engine behind what forecasters call perfect coupling. The door is open, the wind is fast, and Earth stands squarely in the jet. Before we go deeper, a quick note for anyone who loves this kind of journey through space and time. If you're enjoying the story, make sure to subscribe and tap like on Space Historian. It helps more people find these cosmic chapters without interrupting the flow of the tale you're hearing now. The next act unfolds where two magnetic realms meet. Solar wind does not merely graze Earth and slip past. When a fast stream arrives, especially one clocked near 700 kilometers per second, our magnetic cocoon compresses and flexes. The real drama happens at the boundary, the magnetopause, where the interplanetary magnetic field, or IMF, plays the role of a master key. In October 2025, the IMF locked in southward, steady near -12 nanotesla. That orientation is pivotal because Earth's global field points north. Opposite directions invite the magnetic fields to splice together in a process known as reconnection. Reconnection opens a portal, and through that portal the solar wind injects energy deep into the magnetosphere. That energy translates into very tangible effects. Power grids can see induced currents that trip sensors. Satellites feel extra drag as the upper atmosphere puffs up and thickens. Navigation signals grow jittery, and at human-friendly latitudes, the sky itself becomes a canvas. On the night of the 12th of October, curtains of aurora rippled south to places like Michigan and Maine, a spectacle born from the efficient Sun-Earth handshake. In such a configuration, even a modest uptick in speed or a small southward nudge of the IMF can propagate through the entire system like a tug on a web, perturbing currents, steering ionospheric flows, and raising questions that reach beyond the magnetosphere into the realm of global systems. Meanwhile, 3I Atlas is not your ordinary ice ball. It is the third interstellar visitor ever confirmed, and its chemistry reads like a dare to our models. Typical comets born within our own family are ruled by water vapour. 3I Atlas leans hard on carbon dioxide, venting CO2 at a rate nearly 8 times that of water. That fingerprint whispers of the deep freeze far beyond Neptune, of ices built in a sunless pantry we rarely sample. Spectra from scopes on the ground and in space sketch a nucleus, probably smaller than a kilometre across, yet feisty enough to shed up to 4 kilograms per second. At 4 to 5 astronomical units from the Sun, out past the asteroid belt, it already drew a visible hood of gas and dust, the coma you see in time-lapse photographs. The dust it throws off tells a second, quieter story. Instead of fine powder that forms long, delicate tails, 3I Atlas seems to favour coarser grains, chunky and weighty. The consequence is a muted, asymmetric haze rather than a theatrical streamer. Its spin, just a touch over 16 hours, fits the restless tumble seen in many active comets. But the surface recipe, rich in organics with a high CO2 to H2O ratio, remains an outlier. As one mission scientist quipped, this is a messenger from another neighbourhood, carrying a recipe our kitchen has never tried. This uniqueness matters. 3I Atlas is not a curiosity to be filed under unusual. It is a living experiment in how interstellar chemistry responds to sunlight, and what secrets unfold as an alien ice kernel swings through perihelion. And yet, as the solar wind rakes our magnetosphere, a cluster of magnitude 7 earthquakes rolls through the Pacific Rim. The timing lights up social feeds. Claims blossom. The sun did this. The comet did this. The universe is rhyming in a way we've only half noticed. But set the emotion aside and look at the baseline. Over a typical year, Earth sees roughly 15 quakes of magnitude 7 or more. A lively week of tremors can be alarming, but it is not statistically exotic. Mainstream seismology rejects a direct causal road from solar wind to tectonic slip. Decades-long meta-analyses fail to find a reproducible pattern tying geomagnetic storms to quake timing. Speculative papers invoke exotic couplings, ionospheric charge pathways, subtle spin rate modulations, yet none of these ideas have secured the double throne of mechanism plus clear statistical anomaly. As one forecaster put it, extraordinary claims need extraordinary evidence. Without it, science stamps this week's overlap as coincidence, not causation. That debate is more than coffee room chatter. It keeps us honest about how to weigh patterns against noise when cosmic headlines collide on the same page. On the far side of the Sun, 4 broad paths await 3I Atlas, each with a signature that will whisper its choice before the nucleus itself returns to view. The first outcome is the minimalist one, survival. The comet rounds perihelion intact. When it reappears, the measured brightness tracks the pre-conjunction curve, perhaps subdued, but on script. The coma is tight, the light curve is smooth, no sudden jumps. The second outcome is fracture. In that version of the story, coronagraphs, Soho's LASCO C3, Stereo's imagers, the Whisper camera aboard Parker's solar probe, catch a fast rise in brightness, sometimes more than a full magnitude. The single point becomes a string, a breadcrumb line of fragments along the orbit. The dust cloud balloons. The tail kinks or splits. We have precedents. Lovejoy, Ison, beautiful, doomed, marked by sudden flares, bifurcated tails, and multiple pinpricks of light where one should have lived. In violent breaks, a rare sodium tail can flare yellow bright in LASCO's narrow filters, a chemical scream in the data. The third outcome is dormancy. The comet limps out of conjunction, but its engine has cooled. The coma shrinks into an almost stellar point. The tail fades into glare. The brightness curve sags below forecast. If that happens, ground-based scopes may struggle to recover it at all. It is the quiet return of a faint sun grazer, almost invisible, except to a vigilant analyst who spots a mismatch between prediction and reality. The final possibility is dissolution. The comet never returns, not as an object. No fragments, no sustained outburst, only a ghostly dust ribbon and perhaps a brief, unheralded spike in light as the nucleus dies. Each fate leaves fingerprints. A magnitude jump, a sodium surge, a bead string of fragments, or a vanishing act. When the first images drop, those are the signs to hunt. Recovery, if it comes, starts with a single frame. LASCO C3 posts another picture to the Quick Look archive. Every dozen minutes, a new snapshot arrives, and a worldwide guild of comet chasers studies the pixels for the faint wink of 3i Atlas. The first hint might be ambiguous. A speck nowhere yesterday, a modest brightening, a subtle smear against the structured solar background. When anything deviates, an unexpected flare, a double nucleus, a sodium flare, alerts dart through mailing lists and chats like lightning. Then the robots take the baton. Survey telescopes such as the Zwicky Transient Facility and Pan-STARRS cast wide nets, sweeping the region as soon as 3i Atlas climbs out of the sun's glare. These instruments cover huge swathes of sky in a single exposure. Night after night, Difference Imaging software compares new frames against star catalogues, flagging anything that moves or changes brightness between visits. When a candidate pops up, photometry protocols spin up. Observers grab magnitudes through multiple filters, post colors and light curve points in near real time. A steady, predictable rise points to survival. A jagged leap suggests fracture or outburst. And the amateurs, don't mistake the word, play a decisive role. With the right timing, a backyard rig can confirm a professional candidate within hours. Their images, uploaded before breakfast, fill gaps between survey passes. Each positive sighting adds coordinates and brightness to a growing chain of evidence that tracks the comet's reappearance like a heartbeat returning after a long surgery. This choreography, spacecraft triggers, robotic sweeps, human vigilance, is how we look for anything faint and fast. It is the same playbook that will serve us for the next vagabond to grace the dawn. For the moment, countless eyes, automated and human, tilt toward the sunrise, waiting for 3i Atlas to break radio silence. While we wait, the sky offers a consolation prize that is not really consolation at all. For the next 2 weeks, a comet greets the pre-dawn in the east, brighter than most city dwellers would guess, easy to miss if you do not know the trick of seeing it. Comet C 2025, A6, better known as Limon, sails through Cancer before sunrise, an invitation to anyone with a pair of binoculars to watch the solar system move with your own eyes. You do not need a telescope. Set an alarm for an hour or two before the sun, find a clear view low in the east, and scan just above the familiar pattern of the crab. Forecasts put Lemon around magnitude 4 to 5, bright enough to register as a diffuse patch, not quite bright enough to jump out unassisted to every naked eye. Under dark skies, the coma should look like a soft, rounded cloud with a hint of tail leaning away from the sun. The tail will be short, perhaps half a degree, easily swallowed by morning twilight, but binoculars will tease it into view. Timing matters. The coming 14 mornings are prime. Lemon climbs a little higher each day while the moon keeps politely out of the way. By mid-November, the comet will dim and slide back toward the sun's glare. This is the window for a first-time catch. A simple 7x50 or 10x50 binocular, the same pair you might take to a stadium, works perfectly. Even in suburban glow, the comet is findable if you know precisely where to look. Many skywatchers keep a star chart or use a phone app. Some set the alarm for 4:30, pour coffee into a travel mug, and step into their backyard while the world holds its breath. For those who find it, Lemon is more than a smudge of light. It is practice for bigger dramas to come, a way to tune your eyes to faint texture, to learn the sky's rhythm, to join a community that chases these short-lived visitors across the dome of morning. Every glance counts. A quick look, a brightness estimate jotted into a notebook, a photograph stacked from a handful of short exposures. The global record grows one patient observation at a time. The habits you build now, reading the sky, tracking motion against the stars, knowing when to look, will pay off when the next comet or the next interstellar wanderer announces itself. For today, the instructions are delightfully simple. Set the alarm, take your binoculars, look east. The show is free and the ticket is your curiosity. Long after Lemon fades into daylight, the calendar stays crowded. Another visitor, C202R2 Swan, is already getting whispers for reasons beyond brightness. Early in 2026, Swan may crest into binocular range. What sets it apart is the ultraviolet halo around its head, a hydrogen corona first identified by the Swan instrument aboard the SOHO spacecraft. Invisible to human eyes, yet blazing in ultraviolet, that sheath acts like a neon sign for chemistry. Its discovery changed how astronomers trace the earliest steps of water breakdown in a comet's atmosphere. By comparing the light curves of Swan and Lemon, how each waxes and wanes, researchers can tease out the hidden physics behind outgassing, fragmentation, and the slow surface erosion that heat demands of ice. Those twin winding traces, Swan and Lemon, will become templates for deciphering the behaviour of future, stranger visitors we are certain to meet, and the sky's itinerary does not stop with comets. 5 waypoints stand out, like pins on a map for anyone tracking the solar system's restless pace. Late October through early November 2025 marks the principal recovery window for 3i Atlas, when telescopes around the world will comb the dawn for its return from behind the sun. On the 13th of April 2029, the asteroid Apophis will pass so close to Earth that it dips beneath the beltway where geostationary satellites keep their watch, about 32,000 kilometres out, visible to the naked eye over parts of Europe and Asia. On the 20th of September 2040, a planetary parade gathers Mercury, Venus, Mars, Jupiter, and Saturn to one side of the Sun, a rare tableau for anyone with eyes and patience. Farther ahead lies a speculative promise sometime in the 2060 S, a creeping, massive comet flagged in current surveys as a distant slow mover that, if it brightens as some suspect, could rival the great comets etched into history. And in 2177, Pluto completes the first full orbit since we noticed it in 1930, a stately, centuries-long lap that frames the entire modern era of planetary science. None of these dates are trivia. Each is a reminder that the solar system is not a static fresco, but a living laboratory, forever shifting, forever offering the next puzzle. The sky's appointment book is open, and for anyone willing to look up, the list of engagements only grows longer. Wind the tape back to late September 2025. A trans-equatorial coronal hole let fly a 700 km/s stream, stoking geomagnetic disturbances and pushing the auroral oval down to mid-latitudes. At the same time, 3I Atlas vanished behind the Sun, its fate unsigned until late October. Some noticed a cluster of magnitude 7 quakes and stitched a narrative from overlapping timelines. But the seismology ledgers are steady. About 15 such events a year, clusters included, with no proven bridge from geomagnetic storms to tectonic release. Spacecraft, SOHO, Stereo, Parker Solar Probe, captured the critical weeks, but their vantage points cannot yet tell us which branch 3I Atlas chose: endurance, fracture, dormancy, or dissolution. If there are sealed reports on the subject, they have not changed the public record. What is firm is this: the braid between solar physics, planetary defense, and citizen science is tightening, and the next chapter opens as ground observatories sweep the morning sky for the first whisper of the comet's return. In the words of mission scientist Dr. Tamitha Scoff, the Sun's story is written in data, not guesses.